Altogether, it was a list of 223 names. To all of them, I have sent an invitation to help me out through the first stage of my research. And I asked them to answer from a professional point of view to a question proposed as, with whom would you be likely to cooperate from our scene? To all of them, I as well offered this list of 223 names as a reminder or as a guide. From 223 invitations, I have received 63 responses. Through these 63 responses, I was able to create a list of 103 names which were mentioned as an answer to my question. In the end, this is us. If you hear your name, please raise your hand and state present if so. Matija Ferlin, Selma Banić, Sonja Pregrad, Petra Hršćanac, Marijana Krajić, Irma Omerzo, Nikolina Pristaš, Aleksandra Janeva, Maša Kolar, Ana Krajtmajer, Silvija Marčin, Roberta Milevoj, Maja Drobac, Saša Gozić, Pravdan Devlaković, Zrinka Užbinec, Jasna Vinovrški, Natalija Manojlović, Ivana Pavlović, Ivana Rina Sibila, Zrinka Šimičić, Nensi Ukrajinčak, Ognjen Vučinić, Nino Bokan, Tamara Curić, Darija Doždor, Bruno Isaković, Zvonimir Kvesić, Larisa Lipovac, Ana Mrak, Alen Čelić, Dina Ekštajn, Pavle Hajdler, Ivančica Horvat, Ivana Jozić, Maja Kovač, Irena Mikec, Martina Nevistić, Ivana Rončević, Snježana Abramović-Milković, Maja Đurinović, Tomislav Feller, Lana Hosni, Ivana Halc, Barbara Matijević, Goran Sergej Pristaš, Martina Rukavina, Željka Sančanik, Gordana Svetopetić, Marija Ščekić, Andreja Široki, Karolina Šušak, Sanja Trop-Fruval, Žak Valenka, Ivana Vratović, Mirna Žagar, Sven Bahar, Petar Banda, Sandra Banić-Naumovski, Sara Barbieri, Branko Banković, Koraljka Begović, Mateja Biloslić, Ana Marija Bogdanović, Milana Groš, Mila Čuljak, Katarina Đurđević, Kate Foley, Jasna Frankić, Elvis Hođić, Ivančica Janković, Darko Jaković, Marko Jastrevski, Andreja Jeličić, Ida Jolić, Sanja Josipović, Marko Kalac, Tanja Kalčić, Sanja Kocon-Vranješ, Iva Korenčić, Marta Krešić, Zrinka Lupčec, Maja Marjančić, Teja Marsanić, Nikolina Medar, Jelena Mihaljević, Iva Pavičić, Rajko Pavlić, Jasna Periv, Lada Petrovski, Sanja Petrovski, Zrinka Puškec, Nina Sakić, Nela Siserić, Ina Sladić, Melida Spahić, Lana Šprajcer, Luka Švajdar, Ivana Topolovac, Una Vizek, Ljiljana Zagreb, Mija Zalukar, Petra Zanki. Before I continue, I would like to thank to all who have been collaborating on this project.
Hello, and welcome to Star Trek. Let me explain a little bit about what I will be talking here tonight. Tonight I will be talking about stellar evolution, about death, life, and birth of all stars. Some information that will be presented here tonight are broadly known, and some of you might find them familiar. Some information will be presented superficially, and thus some of you might find them redundant. But most of the information will be intentionally twisted and turned in order to fit the story. This story is not completely true. However, not everything in it is a lie. It is a clear, dark, moonless night. You look up into the sky and you see stars arranged in different patterns and constellations. The light from these stars has traveled a great distance to reach the Earth. But what are the stars? How far are they? And are they all the same? In this story, we will look at the fascinating world of stars. We will examine the nature of stars, types of stars, how stars die, and how they are born. If you know a bit about the Sun, you already know a lot about the Earth's nearest star. As you keep following this story, you'll find out even more about what you can see in the night sky. Several billion years after its life starts, a star will die. How the star dies, however, depends on what type of a star it is. There are many ways a star can die. It can happen in a very spectacular manner, or their death can happen slowly and quietly. But why do stars have to die anyways? this is how it all happens. A star needs a fuel in order to live. Once a star is out of fuel, it starts to burn everything within itself. This is called helium fusion or helium burning, depending on the size of a star. Helium is a chemical element with the symbol He and atomic number 2. It is colorless, odorless, tasteless, non-toxic, inert, monatomic gas. It is considered to be the head of the noble gas group in the periodic table. Its boiling and melting points are lowest among the elements, its second highest element and the second most abundant element in observable universe, present at 24% of the total elemental mass. So, while small stars will burn in a flash, big stars will continue to grow and expand because they are capable of burning more heavy elements. So a star becomes big, very big. But as the star begins each new fuel consumption stage, its lifetime in each stage becomes shorter and shorter, and what waits in the end? The so-called Little Bang, a death of a star. So what stands in the way of a star? Not everything goes smoothly and easily for a star. There is a natural force that is threatening to a life of a star. It is called gravity. You may all know that gravity is a natural phenomenon by which all physical bodies are attracted to each other. It is mostly recognized and experienced as the agent that gives weight to physical bodies and causes them to fall down. It is easy to fight it. Only by jumping in the air you are opposing it. A child can do it. But gravity rarely gives up. It never gives up. And it does the same thing to a star. It is always pressuring the star towards inside, causing it to collapse. Sometimes the final expansion of a star sends a shock wave through the star, from inside out. This shock wave ejects all the material of the star, including the core of the star, into the cosmos, leaving behind only a nebula of cooling gases. This is called supernova. Once the star can burn no longer, the star collapses by its own gravity and its iron core heats up. The core becomes so tightly packed that protons and electrons merge to form neutrons. In less than a second, the iron core, which is the size of the Earth, becomes now a tiny neutron. The remains of the core can form neutron star or a black hole, depending on the size of an original star. Some stars, they are very big, too big to become white dwarfs. At the end of their lives, simply disappear and become black holes. Black holes got their names because it seems nothing can escape them, not even light. if an object crosses the event horizon, it's being sucked up into a black hole and can never escape. What happens inside a black hole is unknown. Even our current theories of physics do not fly in the vicinity of a singularity. Well, not everything is that black. Newly discovered information about black holes say that if you have a right distance and the right trajectory, you can escape being sucked up. But, according to his new paper, Dr. Stephen Hawking says that rather than an event horizon, black holes have an apparent horizon. This apparent horizon only holds matter and energy temporarily, and it is eventually released. This idea would reconcile quantum theory and general relativity's predictions for black holes, and solve the black hole fireball paradox that has been plaguing physics for years. Even though we cannot see a black hole, it does have three properties that can or could be measured. It has a mass, it has an electric charge, and it has a rate of rotation. As of now, we can only measure the mass of the black hole reliably by its impact on the objects around it. If a black hole has a companion, it is easier to spot it. From all the matter a dying star emits in the universe, a new star, a new life is born. Without elements produced by supernova, all life as we know it would not be possible. Supernovas see the universe with many elements, including the gold in jewelry, the calcium in bones, the iron in blood, the nickel in our coins, the uranium in the ground, silver, copper, platinum, all were once atoms in stupendous explosions. All elements, essential chemicals for life, were products of supernova. Thus truly, we are the children of stars. So, the next time you will be gazing, remember, you are a product of a star. Stars are massive, glowing balls of gas, mostly hydrogen and helium. But not all stars are the same. Stars come in all sizes, temperatures, and colors. They can be big or small. Some stars are extremely hot, while others are cool. Some stars are relatively close and others are far, far away. Astronomers can measure the distance by using a method called parallax, in which the change in a star's position in the sky is measured at different times during the year. Some stars are alone in the sky, others have companions, and some are part of large clusters containing thousands to millions of stars. When you look in the night sky, you can see that some stars are brighter than others. There are two factors that determine the brightness of a star. There is luminosity, meaning how much energy it puts out in a given time. Distance, how far it is from us. Astronomers classify stars as big or small. Examples of small stars are white dwarfs. Some astronomers consider them to be retired stars. I, however, find them long-lasting stars that have found their way to shine. Other small stars, as astronomers think, which do not shine as bright, are called brown dwarfs, and they are thought of as failed stars. They exist, they orbit around the galaxy, but they do not shine. They do not produce light, and thus they are called failures. Pulsars are yet another type of a star spotted by a waking eye of astronomy. There are also small stars, which are made only of neutrons. They seem to be pulsating, but what they really do is that they produce light only periodically, like a light tower. And this is how we can see them, pulsating. As for big stars, we are familiar with red giants and red supergiants. They are bigger than our sun and they die very fast. This is because they burn what they can in order to stay alive. When they die, they explode really hard. All stars, big or small, tend to make signals. It is a smooth curve on a diagram astronomers have made up in order to be able to track stars' evolution, classify them, and evaluate their significance for the universe and us, the children of stars. For any star to stay alive, it is very important to maintain thermal equilibrium. To stay warm, every star has to burn fuel within itself and thus produce more material that gives it energy to stay alive and keep going on a diagram astronomers have made up. Energy of a star is its ultimate fate. It is a bit odd, but bigger stars, stars with more mass, live shorter than their smaller colleagues. Therefore, massive stars have shorter lifetimes. They live about 10,000 years, while small stars can live up to about 1 billion years. As you have by now already concluded, everything in the life of a star depends on its size, depends on a mass. More mass, bigger the star. Less mass, the smaller the star. Bigger the star, the faster the death. The smaller the star, the longer the life. As in most texts on stellar evolution, we here were discussing life and death of only stars bigger than our sun and those smaller than our sun. Those in between do not get paid much attention here, nor usually, but in spite of not having much catastrophic explosions in their life, they do become somewhat rare objects.
As I have mentioned before, stars are large balls of gases. They are born out of the gases that lie between existing stars in a galaxy. 1. Usually, some type of gravity disturbance happens to the cloud, such as the passage of a nearby star or the shock wave from an exploding supernova. 2. The disturbance causes clumps to form inside the cloud. 3. The clumps collapse inward, drawing gas inward by gravity. 4. The collapsing clump compresses and heats up. 5. The collapsing clump begins to rotate and flatten out into a disk. 6. The disk continues to rotate faster, draw more gas and dust inward, and heat up. 7. After about 1 million years or so, a small, hot, 1500 degrees Kelvin, dense core forms in the disk's center called a protostar. 8. As gas and dust continue to fall inward in the disk, they give up energy to the protostar, which heats up more. 9. When the temperature of the protostar reaches about 7 million degrees Kelvin, hydrogen begins to fuse to make helium and release energy. 10. Material continues to fall into the young star for millions of years because the collapse due to gravity is greater than the outward pressure exerted by nuclear fusion. Therefore, the protostar's internal temperature increases. 11. If sufficient mass, 0.1 solar mass or greater, collapses into the protostar and the temperature gets hot enough for sustained fusion, then the protostar has a massive release of gas in the form of a jet called a bipolar flow. If the mass is not sufficient, the star will not form, but instead become a brown dwarf. Astronomers call them failures. 12. The bipolar flow clears away gas and dust from the young star. Some of this gas and dust may later collect to form planets. The young star is now stable, and it enters the main sequence.